Hello, my name is Joshua Zhao. Here is a YouTube video I made for Electrical Engineering 571 final project. In this video, I'm going to introduce a nano-imaging technique called multiphoton microscopy. Multiphoton microscopy, as is shown in its name, has something to do with multiple numbers of photons. Nowadays, multiphoton microscopy merely represents two-photon microscopy and three-photon microscopy. Although there is non-fluorescence use of multiphoton microscopy, it is mostly used in fluorescence biological nanoimaging. It is a nonlinear process with the use of high-power laser pulses, and it utilizes laser scanning to obtain images. The optical configuration of multiphoton microscopy is almost the same with confocal microscopy, with only a few differences. For commonly used fluorophores, the laser produces excitation light with wavelengths of about 500 nanometer. Being expanded by the beam expander, the beam is reflected by the diachronic mirror and then transmitted through the objective, and finally reach the biological specimen that we would like to image. The fluorophores are excited by the excitation light to emit fluorescence light. The fluorescent light going through the objective is being transmitted by the diachronic mirror this time, and then collected by the detector. In confocal microscopy, a pinhole is used to block the out-of-focus light since the volume of fluorophores is excited in the beam path. Whereas in multiphoton microscopy, a pinhole is not needed because only fluorophores on the focal plane where there is enough number of photons emit fluorescence light, meaning no out-of-focus light to block. Both multiple photon microscopy and confocal microscopy can image at different depths to create 3D volumetric data. But multiphoton microscopy usually has better quality of 3D volumetric data due to its absence of out-of-focus light. Multiphoton microscopy read out data line by line in a raster scanning mode. The optical sectioning produced by multiphoton microscopes is a result of point spread function. In single photon excitation, only one photon is absorbed by the fluorophore, which then emits fluorescent photon that typically has a wavelength slightly higher than the single photon with less energy. The concept of two-photon excitation is based on the idea that two photons of comparably lower photon energy than needed for one photon excitation can also excite a fluorophore in one quantum event. Each photon carries approximately half of the energy necessary to excite the molecule. An excitation results in the subsequent emission of a fluorescent photon, typically at a higher energy than either of the two excitatory photons. It requires that the two photons reach the molecule simultaneously. The probability of the near simultaneous absorption of two photons is extremely low. For three-photon microscopy, instead of two photons, three photons of approximately one-third of the wavelength of the single photon with even higher wavelengths are absorbed by the molecule near simultaneously, which results in emission of fluorescence photon. Two-photon excitation is a relatively old theoretical concept in quantum optics. It was first proposed by Maria Goldberg-Meyer in her doctoral dissertation and observed experimentally 30 years later, shortly after the invention of the laser. One may ask what is required for the simultaneous absorption process to happen. A high flux of excitation photons is typically required for such process. This needs a very high power peak of laser pulses. A mode-locked femtosecond laser can do that. An advantage of multiphoton microscopy is that it images deeper than confocal microscopy. Knowing that the Planck's equation gives energy equals to Planck's constant times frequency. If the excitation spectra of the fluorophores is about 400 nanometer to 500 nanometer, for confocal microscopy, it is the same. For two-photon microscopy, the laser emits light with wavelengths of 800 nanometer to 1000 nanometer. For three-photon microscopy, the laser emits light with wavelengths of 1200 to 1500 nanometer. There is a physics principle called the diffraction of light telling us that the longer the wavelength of the light, the deeper it penetrates because light with longer wavelengths could bypass more obstacles on the light path. In biological imaging, the deep tissue is highly scattering. The single photon from confocal microscopy has shorter wavelengths, which results in shorter penetration depths, whereas two-photon or three-photon from multiphoton microscopy have longer wavelengths, which can penetrate deeper into the tissue with less scattering. Another advantage for multiphoton microscopy is that for commonly used fluorophores like GFP, the maximal emission wavelengths and the maximal excitation wavelengths are typically very close to each other, which is comparably harder to separate than using two-photon microscopy or three-photon microscopy. Their wavelengths are 2 times or 3 times greater than that of the emission wavelengths, which is much easier to filter out to obtain a high SNR ratio. Overall, multiphoton microscopy has some advantages on biological imaging. It could image deeper with 3D volumetric data. It only excites the fluorophores on the focal plane. It has less scattering light and out-of-focus light with a high SNR, and it could reduce photobleaching effect and phototoxicity. Thank you for watching this YouTube video. See you next time.